Today we will discuss about directional coupler. And a method called coupled mode theory. That can be used to study the properties of directional coupler. Directional coupler is a very useful device in integrated optics. So, the structure is like this. There are two waveguides which are very close together. There are two waveguides which are very close together. The cross section can be expressed like this. So, when light is launched into the first waveguide, it is possible to couple or transfer light from the first waveguide into the second waveguide. So, we can change the parameters like the spacing of the waveguides or the length of interaction or the refractive index delta n between the waveguide and the substrate and so on to get different properties of this structure. So, in order to study the properties of this, we use what is called the coupled mode theory. So, basically we have to address the we have to solve the scalar wave equation corresponding to this refractive index profile corresponding to this directional coupler. So, we have to solve the wave equation for the field distributions and of course, we have the refractive index profile to be more complicated than what we have seen earlier. So, let us consider the 2D version of this directional coupler. So, we have been following a scalar approach. So, the extension to the vector is of course possible and straightforward, but more complicated. So, let us consider a two dimensional form of this directional coupler. So, recall that we can use the effective index method to convert from the 3D geometry that is given to a 2D configuration. So, the 2D configuration is like this. So, we have two waveguides very close together, waveguide 1 and waveguide 2, and this length is important, as I said. This is the length of interaction and we have the refractive index of the first waveguide as n1 waveguides. They can be different, two different waveguides. So, the widths can actually be different and there is a spacing, we will say the spacing to be s, and of course, the waveguide width w1, waveguide width w2, the corresponding, we know the properties of the individual waveguide because these are symmetric slab waveguides, and we will assume that the propagation direction to be z and the waveguides are aligned along the x direction. This is the geometry that we can use. So, the refractive index profile can be written as follows: along the x direction this x direction. I will take the origin to be the middle of this structure, and the refractive index is N2 in the substrate. So, we can write the refractive index profile as follows. Origin, the spacing S, the width W, and so on. So, this is N1, refractive index in the core is N1, outside is N2, and of course, 0. So, it is possible to solve this problem as a multi-layer waveguide problem by applying the boundary conditions, etc., as we did for the symmetric slab waveguide and asymmetric slab waveguide. But of course, this is more complicated, and writing the equations in each of these regions and matching the boundaries and manipulating the equations is quite involved. And of course, one of the purposes of choosing this problem is to introduce what is called a coupled mode theory, which will solve this problem in a very simple manner. And of course, the coupled mode theory has got many applications, can be used for many other purposes, as we will see later on. So, in the scalar approach, we express the mode field as a superposition of the individual waveguide modes as follows. So, it is assumed that the individual waveguide modes are known. So, we can say that the individual waveguides have their mode fields known, because we can solve them as we have done earlier. We can solve for the propagation constants and the mode fields, etc. So, individual mode fields of the waveguides are known. So, in scalar coupled mode theory, we express the mode field, the entire mode field of the structure as follows, as a combination of the mode fields of individual waveguides. Let us say psi of x comma z is the field that we are trying to evaluate, and this is expressed as a linear combination as follows: A of z into psi of x, psi a of x into e power minus I beta a z plus b of z into psi b of x into e power minus I beta b z. Where psi a and psi b are the individual mode fields, and beta a and beta b are the corresponding propagation constants. So, the coefficients a of z and b of z are z dependent and represent the variation of the field and the exchange of power between the waveguides, etc. Just as an example, if A equals to 1 and B equals to 0, at z equal to 0, it implies that psi of z is psi a of x, and the whole field is the whole field, the power of the whole of the field is concentrated only in the first mode. Similarly, at z equal to, at the end of the waveguide, if you say that a of z equal to 0 and b of z equals to 1 at z equal to L, it implies that the whole power is in the second mode. You can say that the whole power has transferred into the second mode if we get such a outcome. So, the crux of the problem boils down to evaluating A of z and B of z, since we said that they are functions of z, it implies that the power is exchanged between the first waveguide and second waveguide, and we need to evaluate how they are exchanged. So, let us start with a scalar wave equation and substitute for the mode field and evaluate. So, the scalar wave equation for the whole field is given by del square of psi plus k0 square n square psi equal to 0, where n is the refractive index profile n x comma z, and the operator has x variation as well as z variation. Now, expressing the total field in terms of the individual mode fields, we get psi of x comma z is A of z into psi of A of x into e power minus I beta A z, and B of z into psi b of x e power minus I beta b z. We are considering two arbitrary waveguides which may have different propagation constants. So, let us differentiate d psi by d. See, the equation contains d psi by dx and d psi by dz. So, we have to evaluate each of these. So, d psi by dx is simple. E of z e power minus I beta A z multiplied by d psi A by dz, and B of z into psi b of x power minus I beta b z into d psi b by dz, and the second derivative is also needed in the expression. Okay, because psi is a function of both x as well as z, let us use d square, dou square by dou x square, dou square by dou square by dou x. Next, we need to differentiate psi with respect to z 2 times. D psi A by dz multiplied by e power minus I beta A z plus minus I beta A into A into e power minus I beta A z. So, derivative of e power minus I beta z results in this factor. So, the entire thing multiplied by psi A. Similar expression for psi b. Now we need the next derivative of this, d square psi by dz square. So the second derivative with respect to A plus retaining dA by dz and differentiating this, that means same term. So we can write it as d psi A whole square into A e power minus I beta A z, because already one term is there, you can just set double of that, plus no square is not there, plus differentiating once again this factor minus I beta A whole square into A into e power minus I beta A z plus the corresponding factor within terms of b, d square b by dz square into e power minus I beta b z plus 2 into minus I beta b into b, just a minute please, this has got a second derivative dA by dz, dB by dz. Into e power minus I beta bz plus minus I beta b whole square into b into e power minus I beta bz of psi b. Of course psi A has to be there here. So the expression for d psi by dz and d psi by dz square. So just to you can see the expression of psi differentiating with respect to x. So all this we need to put in this wave equation and simplify. So before we go further, we will try to see if some of the terms can be neglected. So we have the second derivatives and first derivatives with respect to z. So if we consider the factors a of z, dA by dz and d square A by dz square, and how fast or slow they vary, we can neglect some terms. For example, if the variation is very slow compared to beta, we can say that the second derivatives can be ignored. So just we will make a simple calculation and check whether they really are they can really be neglected. For that purpose, let us consider some simple form for A of z. Let me say that A of z varies as cos kz. This is just as an example to test or check whether the second derivative can be neglected. So if you say A of z goes as cos kz, dA by dz will go as k times cos kz k times sin kz, and d square A by dz square will go as k square cos kz. So we will look at only the amplitude parts and say that A goes as the unity, and so I will put just the squares of it. Goes as 1 or something proportional to k, and the order of magnitude for this is k square. And also if we look at the equations, we multiply that we note that the second derivative is going as 1, the first derivative is going as proportional to b, and the second derivative is this not b. Let us look at once again. The second derivative is going as 1. I will use some other color for this. So, this is multiplied by 1, the first derivative is multiplied by beta, and the second derivative is multiplied by beta square. So, if we say that beta is, I am just very rough calculation I am doing to check whether some of these things can be neglected. Beta, as you know, is 2 pi by lambda into n effective, and lambda is of the orders of wavelength of light is, let me say, communication wavelengths 1.5 microns. So, you have beta going as around 6 by 1.5, refractive index also of the values of 1.5. So, this is of the orders of 6 radians per micron. And then beta square, if it is appearing in any of the expressions like the constant beta square. So, beta square will go as say 36 radians per second per micrometer, and then this is multiplied by the value of k. Suppose let us assume that the interaction lengths are of the orders of a millimeter. Suppose I have L of 1 millimeter. So, the k into L, k into L, the periodicity. So, we can say that k is of the orders of, typically periodicity of pi, we take pi by 2 pi or pi by 1 millimeter. So, k is of the orders of 3000. Per micrometer. So, k is of the orders of 3000 per micrometer, which multiplies this beta. So, we say the product beta into k is of the orders of 18,000 radians square by micrometer square. This is of the orders of 36 radians per micrometer. And when you have the second derivatives, they are multiplied by k square. So, k square goes as 3000 square radian square per micrometer square. So, this is of the orders of 9 followed by 1, 2, 3, 4, 5, 6. So, now we can guess what are the typical values involved, and we can say that these second derivatives are very slow and can be neglected. So, all this argument of typical calculation is to assess that the second derivatives could be neglected if the coupling is very slow. So, we will reduce this and then substitute into the original wave equation and evaluate. So, this is the original wave equation to evaluate. So, the original wave equation can be written like this. When we substitute a of z into e power minus I beta a z multiplying d square psi a by dx square minus beta a square psi a square plus k 0 square n square of psi a, and the other factor beta z power minus I beta b z d square psi b by dx square minus beta b square into psi a square plus k 0 square n square psi b square psi b plus, I will put separately once again, 2 I beta a to dA by dz multiplied by psi a multiplied by minus e power minus beta a z minus 2 I beta b d beta by dz and multiplied by psi b minus e power minus I beta b z equal to 0. I have grouped the terms such that you can observe and interpret and take action on these each of these terms. So, here as you know we have neglected d square a by dz square and d square b by dz square compared to dA by dz terms which have got beta a along with them. So, compared to them, so the individual waveguide modes are grouped in these terms. As you know, d psi a by dx or psi a and psi b satisfy individual waveguide modes, which means that if you have a refractive index profile like this for the each of these modes, refractive index profile N A, let us call it N A and N B, which has got N1 here and N2 at this boundary, NB, and the actual profile is like this, the given refractive index profile. So, we can say that the given refractive index profile n of x can be written as a combination of NA and NB like this. N of x can be expressed as n of a function of x plus delta n a of x, and n of x can also be simultaneously be written as n b of x multiplied by a perturbation delta n b of x. Let me explain the terms n a and n b. So, this is a given refractive index profile, and if you say that this is the refractive index profile for the n a, this extra term will be something like this. So, in the same scale I will put with red delta n, let me say this is n, this is n, delta n a will look something like this. That means it has got a value of n a let me call just I will put delta n only. So, if you say let as an example, let me say n1 in the core region and n2 in the cladding region, this is delta n equals n1 minus n2 and 0 value all over. So, the refractive index profile of delta n a will look like this. All over the place it is equal to 0, and only in the area of n b, this is the area of second waveguide, in the place of second waveguide alone there is a delta n value equal to 1. So, similarly for n b we can say that n b will be looking like this. So, in the area of n a it is equal to n1 minus n2, and in all other places it is equal to 0. So, this is called the perturbation to the n a, and this can be called as perturbation to n b, and it is occurring only in a region which is in the other in the area of other waveguide. So, if you look at this equation, if instead of n, if you have n a, we can observe that this goes to 0. So, instead of n we can replace with the delta n a and then replace this entire thing by delta n a. So, what we get is, I will simply put here this entire note with a different color. I will put with a different color. All these things I will replace by delta n a. Of course, I would like to once again emphasize extra point that most of the time you have n a squares in your equations. So, I would say that I would represent the perturbation in terms of the squares of the refractive index rather than just NES. So, if I want to replace this factor, I can replace by delta NA square psi A, K0 also of course there. K0 square. Similarly, I will replace this entire factor by K0 square, I will use a different color, K0 square delta NB square psi B. So, the final expression looks like this. I will use a different color. Plus the other remaining factors as they are. Minus. At this point, I would like to introduce an idea called a clue that we take from what is called the orthogonality of modes. Orthogonality of the modes implies if you have a modes psi p and psi q corresponding to the same waveguide, psi p and psi q are two modes corresponding to the same waveguide, then they are orthogonal, meaning that the overlap factor of psi p multiplied by psi q will be complex conjugate star over the entire cross section equal to either 0 or 1 depending on the whether talking about the same modes or not. For example, if it is this equal to 1, delta pq equal to 1, if p equals to q and is equal to 0 if p is not equal to q, which means if the modes are different then their overlap factor is 0. This is called the orthogonality principle. And of course, most of the time the fields are orthogonal or normalized to 1, their overlap factor to be 1. So, then they are called orthonormal. So, the clue to take the overlap of the fields comes from the orthogonality of modes, which has got many applications and is very general in nature for any arbitrary types of waveguides and so on and so forth. But at this point in the study of the directional coupler and coupled mode theory, we take the clue that the overlap of fields can be very useful, even though the orthogonality principle is not rigorously applicable to directional coupler, because the modes psi A and psi B do not correspond to the modes of the same waveguide. So, taking this clue, we will multiply the first expression, the expression that we have derived here. This expression is the one we are trying to manipulate, and I will try to multiply this whole expression by either psi A or psi B and integrate over the entire cross section, so that the terms which are cross psi A overlap psi A multiplied by psi B etc. will go to 0, and the modes which are psi A multiplied by psi A star will be equal to 1. There is some small error here, will change, it is not square, psi A only. So, if you multiply this whole expression with psi A, so the factors are, there is a psi A here and there is a psi B here. When you multiply with psi A, this will go to 0 and this will be multiplied by psi A psi B, so it is not going to be 0. Let us see what comes out. So, I will rewrite this expression again, or so first step I will use a different color to multiply and then later on erase. So, multiply by psi A and integrate psi A star and integrate. So, there is a psi A star multiplication here, there is a psi A star multiplication here, and there is a psi A star multiplication here, and here also psi A star. So, we observe that here is psi A psi B combination and here is psi A psi B combination, and we can apply the orthogonality here. Whereas here we have delta NA psi A and psi A, and the integral of this will not be equal to 0 because delta NA is multiplying and is also a function of x. Similarly, here psi B and psi A are there multiplied by NB and the integral of this. So, this also will not go to 0. We can say that we can approximate this factor to be 0 and the second derivative of B is going to be eliminated, and we have an expression dA by dz depending on A of z and B of z. That is what I would like to write now. dA by dz written in terms of, I am simplifying and writing the final expression, you can work out and then cross check, and of course I am using the two constants KAA and KAB so that all the factors could be clubbed into that. The final form is correct. Into B of z multiplied by e power minus I delta beta into z. Let me use plus for this. So, where, of course let me write the second equation also and then we will interpret what are these factors, and for the variation of B, d by b dz will be given by minus I kBA into A of z into e power I minus delta beta into z minus I kBB into B of z. Let us spend a little bit of time to understand this. The constants KAA, KAB, KBA and KBB contain the factors of overlap. So, I will try to use the previous expression to manipulate and then show that once again. So, I will erase unnecessary fields and then try to manipulate this equation. So, you have A of z multiplied by K0 square and a delta NA square. So, and here you have 2I delta beta A. So, we'll do this goes to 0, and this is divided by this, and you have I have multiplied throughout by e power minus I beta a z. So, this will not appear at this point. So, the final equation is like this. So, the k a a I will write a general expression k p q, let me say, representing all p and q can be a and b's, can be expressed like this: k 0 square by 2 beta p into, you must have the integral with respect to delta n a should be there in the expressions, and psi, no, we have been writing in terms of a and b. So, let me put in form of p and q, p psi p psi q star ds, and of course, the integral with respect to, or let me call it as x only for the time being, dA dx psi q dx psi a star dx. I hope this is representing the, and also maybe minus. Lot of minus signs are there, all the minus signs could be coupled into the constants. So, this is correct. Okay. So, minus signs are added. I is already we have used here. So, that is not necessary to be there in that, and these are all positive. So, these coupling coefficients, so the so called coupling coefficients are constants depending only on the refractive index profile, the perturbation to the refractive index profile, the waveguide dimensions, and so on and so forth. And beta, delta beta, the factor delta beta is what is used here, is beta b minus beta a. Let us note, in one place it is plus and the other place it is minus. So, these are quite general and is applicable to many types of waveguides. Let us simplify further, taking a specific example. So, I would say that let us examine the nature of the constants KAA and KBB with respect to KBA and KB. So, we have the delta as I described earlier. We are integrating over the region of perturbation only. So, in the case of psi a, we have the mode field psi a, let me use some other color, mode field psi a, the mode field, once again one more psi a because we have multiplied there, and the delta n a which is in this region. In contrast to that, the constant k a b is containing the mode field psi a, the mode field psi b which is in this region, and the perturbation delta n a. So, the product of delta n a, psi a and psi b is what is appearing in k a b. The product of psi a which is very small here, and once again psi a which is again small here, and another small quantity is there here. So, we can argue that these coefficients are small compared to the other two coefficients, and we get a very simple set of differential equations for the mode fields. So, I will quite quickly write again dA by dz is minus I k a b into b of z and e power I delta beta z. dB by dz is I minus I k b a of z into e power minus I delta beta z. One is plus and one is minus, whichever way you define the delta beta. So, these are called the coupled mode equations. We made several approximation. Please check your derivation and note all the places that we have approximated and the reasons for that. Let us apply this for a simple case of a directional coupler consisting of two waveguides. I will not evaluate the coupling coefficients A and B right now, but let us see what happens to the solution when it comes. So, when the waveguide 1 and waveguide 2 are identical, we have a directional coupler consisting of two identical waveguides. So, we can say, we can call this as a symmetric waveguide directional coupler and check what happens when we launch light into the first waveguide and when you receive the light from the second waveguide. So, when waveguide 1 and waveguide 2 are identical, you have beta A equals beta B, and so KAB equals KBA and delta beta equal to 0, delta beta is 0. So, you have the very simple form of the differential equation for the variation of the field injected into the waveguides. Ik multiplied by B of z and dB by dz equals, let me still use minus I k E of z. This could be solved easily by differentiating the one expression and putting it into the other. For example, I replace B into this. So, I will differentiate this with respect to beta 1s and substitute. So, you have d square A by dz square equals minus Ik dB by dz. So, minus Ik can come over this side, and for dB by dz I can replace with minus Ik E of z, and so we have d square A by dz square plus this k will go that side minus and minus and k square A of z equal to 0. This is a very simple equation which we know, and the solution can be written in terms of cos and sine. A of z equals C1 cos kz plus C2 sin kz, where C1 and C2 are arbitrary constants. So, we will quickly evaluate them by using the initial conditions. So, let us say the light is launched into the first waveguide and not into the second waveguide. So, that of course, we need also the expression for B, which we can get from the first expression. We can substitute for VA into this and get the expression for B. I will write somewhere here. So, B of z can be given as minus Ik into d by dz. So, minus k sin kz C1 included plus k2 k C2 cos kz. This case will cancel out with this, and you get I will go to both side and we can make it plus I sin kz minus I cos kz, and these arbitrary constants still remain. When we apply the initial conditions, we can eliminate and get what are these A and B. Let me quickly do using. So, let me say A of z equal to 0, A of z equals to 1, all the light is there in the first waveguide, and B of z equal to 0 as I mentioned in the beginning at z equal to 0. So, substitute z equal to 0 in this and A z equal to 1, and we get C1 equal to 1. Similarly, substitute B of z equal to 0 in this expression, and we will get C2 equals 0. So, we can say that the solution for this is A of z equals to cos k z and B of z is minus I sin k z. So, I will plot the amplitudes to see what happens. So, let me say this is the z propagation direction, here are the amplitudes on this side. So, this is going as a cos. I will put only the magnitudes to illustrate. These are not very and this goes as a sine and so on. So, this is the magnitude of B and magnitude of A. From this we observe that when the field is maximum here, the field is minimum here, no field in the second waveguide, and the field when it goes to 0, it can go to 0 by a length called coupling length, and the like is maximum in the second waveguide. So, by the use of this analysis and this study and the coupled mode theory, we can say that there is a periodic exchange of power between waveguides with a periodicity of pi. So, is going back is the periodicity of pi. If you choose the directional coupler length to be L, which is equal to k into L, if you choose it as equal to pi by 2, this is a pi by 2 point, we can say that all the power is exchanging to this. So, the coupling length necessary for crossover can be called as pi by 2 k. So, if you choose the length of the waveguides to be equal to pi by 2 k, then you can get the crossover state of the directional coupler. So, all the power is going into this L, I will put with a cross equals pi by 2 k. Now, of course, you can observe many other things. For example, it restores to the original situation after length L equal to pi, and once again at L equals 3 pi by 2 also you have a crossover state, and so on and so forth. There are several interesting features. For example, if you choose the coupling length to be half of this pi by 4 for example, then you know at this point the field is 1 by root 2, cos kz is 1 by root 2 and sin kz is also 1 by root 2, and you can say that the power is divided equally, powers which are proportional to a square and b square. A square and b square can be thought of representing the power, and power is half. So, power is divided equally if you choose the length L cross by 2. So, in conclusion, we can say that directional coupler is a very useful device. I would just like to mention that in optical switches we can change the delta in the refractive index by using external fields, and we can switch between the crossover state and the bar state by using external electric fields. We will come over to these after a few more classes. So, finally, to summarize, directional coupler is a device that can be used to exchange power between waveguides, and there are many applications.